Yeah, there are actually going to be no fail screens in this talk, just for variety. So we have this rather interesting situation, and anybody who's been around for more than a few years and taken a step back and looked at the trends will notice that underneath constant change, there is a kind of silent and very steady continuity and constant lack of change. And so this is the premise here. Old is the new. I find that although I'm not necessarily keeping up to date with every single technology, because that's actually not possible anymore, what I find is that I can actually have an informed understanding of a surprising amount of things by saying, what is this like, and therefore what are the differences? What are the things I actually need to concentrate on? And you also find that you're able to then pass on these pearls of wisdom, and people go, oh, I've never seen that before. And you can go, yeah, it's a really new idea back in 1972, or this was 1974, and this kind of thing. So this is what I want to explore. And André Gide, this lovely quote, everything has been said before, but since nobody listens, we must always start again. Because there's something else in software that we are particularly bad at. We have a very weak sense of history. So it is not simply that we keep rediscovering and reinventing the wheel, and eventually we might actually make it round. It's that we have a very poor cultural sense of history. And so we live in a constant state of astonishment and rediscovery. And I'm not saying that that's necessarily a bad thing. Well, no, actually, maybe I am. Well, I'll let you decide. So let's figure this one out. Let's go back. So we're going to talk history. Let's see, last week, Shakespeare Day. It turns out that Shakespeare was one of the first programmers. And, this is a little-known fact. Clearly, the lack of appropriate hardware back in Elizabethan times was a little awkward. So he would write these scripts, and he had to use the actor model to kind of execute them. But many of his plays are actually carefully disguised commentaries on issues that we may be familiar with. So, for example, The Tragedy of Hamlet, Prince of Denmark, is actually a play that is entirely about memory management. Oh, you don't believe me? You're thinking, oh, it's just that quote. No, look, here's Ophelia. Ophelia is talking about manual memory management, malloc and free. 'Tis in my memory locked, and you yourself shall keep the key of it. On the other hand, Hamlet's all about garbage collection. Yea, from the table of my memory, I'll wipe away all trivial fond records. Okay, records, okay? Not a new idea. There's a whole load of database migration stuff littered across the place. So you've got this, and you might think, oh, well, these days we're all about garbage collection, and garbage collection is a really new idea, and all the rest of it. And then somebody kind of says, oh, wait a minute, Lisp. Lisp is sometimes misattributed as a language of the 1950s. Its first implementation was 1960. I'm only going to take things that run. Things that are on paper do not run. So although it was sketched out in the late 50s, the first working implementation was 1960. And that had garbage collection. And so, oh, well, Lisp was kind of all, that was a niche thing. That was functional programming. Nobody else was doing it, except, of course, Algol 68. And the clue to the year is in the name. So this is my copy of the Lisp Programmer's Manual, one of my most treasured possessions, and I've got the Algol 68 manual as well. I do love a good old book. And Algol 68 at the time was considered to be a large language, too complex and ambitious to be implemented, and is now smaller than almost any language that you are using. You can actually find online implementations of it. Algol 68 is the most influential language that few people have ever heard of or used. It gave us such wonderful things as the abbreviation of int. Everybody else in the 60s was happy with the word integer, but not Algol. Now, we're going to knock that down to int. We're going to have char, we're going to have long, we're going to have short, we're going to have struct, we're going to have union. We're going to have, in fact, this is a procedural language, and it gave us, and people often think procedural, that's just another word for bad. And it's like, wait a minute, so let's look at the characteristics of Algol 68. It was expression-oriented, not statement-oriented, so therefore everything yielded a value. You didn't have to have two different syntaxes for if statements, one for expressions and one for, oh, okay, this is sounding kind of familiar. It had if and phi, if you ever wondered where that came from. It came from here. It allowed you to pass around anonymous procedures that captured their variables by closure. Oh, so in other words, lambda expressions. This was procedural programming. Something terrible happened in the 1970s. We shall look into that. So this was state of the art, and it was garbage collected. 1967, Simula 67. Again, the clue is in the clue to the year is in the number and the name. That had garbage collection. So this is really not a very new idea. And really what I want to explore here is this idea of ideas that are not new. So I've got my name on a couple of books to do with patterns, and it's worth understanding what patterns are. A lot of people think patterns, and they think, oh, patterns, they think singleton. There is a good singleton. Well, in fact, there's two good singletons. There's the singleton that attracts consultants. Hello. I'm available to help you with your singleton problems. And then there is the singleton that is actually good for your code. That's this one. It's a single malt. Okay? And when you sip it, when you have a dram of this stuff, you pause for a moment and you think, you know what, as that kind of fire rolls around your mouth, maybe I won't put that really big global variable in the middle of my code. And you have that moment of kind of like oneness with the universe, and your code is improved just simply through inaction. So that's the singleton that you want. By the way, curious observation. In my experience, a system either has 0 or 2 or more singletons present. Never one. Uncanny. So what we're really talking about is something a little bit deeper. A few years ago, when everybody was going through manifesto craze, I got a bit upset by this, or a bit pissed off, and I was running a workshop at a company where we were actually trying to pull out, what are your patterns? Not the patterns that we find in books, but if I were to join your team on Monday, what things do you do, perhaps, that I am not familiar with? What's normal around here? What is your vernacular architecture? So we were looking at this. So I just put up on the whiteboard, Patterns Manifesto. If it had a manifesto, it would be this one. We are uncovering better ways of developing software by seeing how others have already done it. But simply, as Brian Foote said, patterns are an aggressive disregard of originality. It is the idea that most of what we build is unoriginal and should be. The little bit of originality is the bit that you want to really labor at. It turns out most problems have been solved, and we're very poor at communicating those. So, related to this, one of the key members of the patterns community, Dick Gabriel, wrote this book in the mid-90s. It's a collection of essays. It wasn't just about patterns. Some of his reflections on software development, software as an industry, and so on. And he collected together a number of these thoughts. And one of the more interesting ones is this one. In 1990, I proposed a theory called worse is better. Now, I'm just going to pause for a moment. I have to do this every time I put this slide up. Worse is better is possibly the worst name that he could have come up with it. And there's a sort of it's self-referential in that respect, I guess. There's also a sort of a humor here and an irony. One of the hardest things in software development is naming things correctly. We are so bad at it, and this is an example. Because when you hear worse is better, you think, oh, I'll just put out any old crap and that'll be good enough. No, that actually has a name. That's called good enough software. The good enough school of software is actually quite different. So you need to really understand what Dick was saying, and obviously it turns out people had really bad attention spans even during the 90s. It's not a modern phenomenon. So let's actually look at what he said, and let's find out what he meant by worse. It was kind of like partly a joke, partly a play, if you like, of why software would be more likely to succeed if it was developed with minimal invention. In other words, take what you know and do something else with it. Add the bit that people don't know. It is far better to have an underfeatured product that is rock solid, fast, and small. Now, when most people think worse, they do not think of these three qualities, you know? So, yeah, I'm going to do worse is better. Oh, right, yeah, it's going to be absolutely bulletproof. There are no bugs. Okay, your idea of worse is very different to my idea of worse, yeah? And it's going to be fast. Oh, I thought it was going to be slow and buggy. And, I thought it was going to be large and bloated, but no, apparently small is worse. No, the worse is a judgment on the last aspect here, rather than one that covers what an expert would consider to be the complete requirements. It's about minimal requirements. It's about focusing on the smallest scope. And this theory is elaborated and explored a number of times throughout the decade. And I was involved in a panel at OOPSLA 2000 on the worse is better front. But the whole thing started back in 1990, which predates not only what we call agile development, but also rapid application development and a whole load of other stuff. And the characteristics, simplicity, that one never goes out of date. We keep having to say it because nobody's listening. But he had an emphasis here. The design is simple in implementation. The interface should be simple, but anything adequate will do. In other words, it needs to be sufficient, not stupid, not terrible, but it doesn't have to be awesome, because it turns out if your implementation is simple, then it has a very important property. You can discard it. You can replace it. Okay? You can change it. You can understand it. And that turns out to be one of the most important properties of this approach. Completeness. The design covers only necessary situations and can be sacrificed in favor of any other quality. One of the classic examples of this is Ward Cunningham's wiki. The original wiki, so here's the sort of generated Perl from it, is this is the top and tail of the original wiki Perl file. It's 150 lines of Perl, for heaven's sakes. I mean, that's not even comprehensible to humans. So, if somebody comes across this, it'll be a far greater mystery than hieroglyphics in the future. I mean, it's a terrible language. But 150 lines of it, you know what? If you can get away with that, and I want you to just imagine if you've got a team to do that. If instead of getting somebody like Ward Cunningham to go, oh, you know what? I want an editable web. I'm going to just try this really simple thing, and I'm going to introduce a few conventions. I'm going to keep it really light. And, it's not perfect. It's not complete. But I've got it up and running. And I used to hang out a lot on the c2.com wiki, the original wiki. And it was great. It was just enough that you need. And we have MediaWiki. We've had everything has expanded from that. It's so small that you can rewrite it. It's so small you can write your own. But it's also got massive potential for extension, as we can see with something like the full infrastructure behind Wikipedia. So if you imagine offering this to a team at a company, they'd spend 18 months and not come up with 150 lines of Perl. Oh my goodness. It would just dwarf any Java project you've ever experienced. So there is this thing of let's just start small. Because if it's small enough, we can change it. If it's good enough, we can modify it. So, yeah, we can keep it small. Correctness. The design is correct in all observable aspects. Do it right. Consistency. The design is consistent as far as it goes, but it's less of a problem because you always choose the smallest scope first. So in other words, this is actually an incremental approach. The use of the word first here is really important. You're going to do this, you're going to come back to it, you're going to add things, you're going to throw things away. So there's a really interesting kind of perspective here. Now, what we've just done here is discovered that the design process is an iterative one. And you might be thinking, okay, well, Dick was talking back in 1990. So that was a bit of a revelation, was it? No, the design process is an iterative one. Andy Kinslow. That's taken from this document. The clue is in the number, 1968. Welcome to the half-century anniversary of the NATO Software Engineering Conference. It's 50 years. How are we doing? We've discovered that design process is an iterative one. How's that working out for you? Yeah, new idea to you? Yeah, for a lot of people, it's absolutely refreshing. And yet, and there is this notion, sometimes people misattribute this. They say, oh, okay, this conference in Garmisch created the term software engineering. Actually, no, as best as we know, it was this woman here, Margaret Hamilton. She worked on the Apollo flight systems, and it was in the earlier to mid-'60s that she coined this phrase. And she developed really kind of crazy cool ideas like fault tolerance, which actually allowed the mission to go ahead. I began to use the term software engineering to distinguish it from hardware and other kinds of engineering, yet treat each type of engineering as part of the overall systems engineering process. Her idea was that engineering was everybody's at the table. Okay, there's kind of no hierarchy, and that was her perspective. But a lot of people go, well, wait a minute. This is all about plan-driven development, isn't it? Isn't that what we were taught? Isn't this what the document was filled with? Yeah, it's filled with classic statements like this. Douglas Ross, the most deadly thing in software is the concept, which almost universally seems to be followed, that you are going to specify what you are going to do and then do it. And that is where most of our troubles come from. This was not news in 1968. This was no great discovery. We didn't have to wait for Royce's paper in 1970, which is often misattributed as being the origin of the waterfall process. The point here is we knew this, and the hardware and the interaction that we have in terms of programming has changed radically, and yet it was already a known thing. Now, I'm not going to say that everybody knew everything back in 1968, but when you read through the proceedings, you get a real sense of variety of thought, just as we have these days. Not everybody was of one mind, but there's an awful lot of stuff on these lines. As I say, 68 was a good year. The Fall Joint Computer Conference, 1968. There's a lot of details in here. The one that I'm going to focus on briefly here, Research Center for Augmented Human Intellect, D.C. Engelbart. This is the mother of all demos by Douglas Engelbart. Very, very influential. He showed crazy ideas like dynamic linking at runtime, which turns out to be quite important for modularity, video conferencing, the mouse, and stuff like that. Very, very influential. People in the audience included people like Alan Kay, who went on to develop Smalltalk systems. And there is this idea here of 68, good year, good year. So let's go back to the future, 1990. Implementation characteristics of worse is better. The implementation should be fast. Turns out that's quite important, especially back in 1968, if you're going to write mouse drivers, because nobody's done that before. You need things to be fast. It turns out that speed is one of the most important critical qualities that is overlooked, because a lot of people misunderstand the guidance on performance. Let's put it this way. If you want to improve the usability of any system, making it faster gives you that for free. It's not just changing colors. You can change the colors, you can move the buttons, but if you make it faster, so fast that nobody notices, then you've suddenly got an improvement in usability. You no longer have to have a debate about what color and what logo or symbol you should use for the weight cursor. It's gone. There's nothing there. Which means, this is interesting, that performance should always be a concern. It's not something you do at the end, because we have no end in an incremental approach. My favorite piece of advice from the mid-90s, remember there is no code faster than no code. Until somebody invents a tachyon pipeline in the processor, this will remain true. But we also have this other observation going back into the 80s. The fastest I.O. is no I.O. And this is one of the most overlooked things. I did this with a team where it turns out we got a threefold speed up in something they had managed to only get a 10% improvement over 2 years simply by eliminating unnecessary I.O. It was just a case of why are you storing this? Why are we not keeping this in memory? And this is something we need to remember, because everybody's got this habit these days of shoving things out on the network. So one of my favorite blogs of 2014 was this one by Adam Drake, one of those wonderfully descriptive titles. Command line tools can be over 200 times faster than your Hadoop cluster. So he wrote this big data, well, not big by modern standards. Big is a moving target. Big is just simply a way of, it doesn't fit in memory. But that doesn't roll off the tongue, so we use the word big. But he chose this 2 gigabyte problem, which you're saying, well, good grief, on my current laptop, I can run that in memory and still have space to look at pictures of cats, you know. But you go back to the end of the 90s and you tell somebody you've got 2 gigabytes of memory, they're just going to sputter into their coffee and go, I'm sorry, that's not happening. Big is a moving target. It also means your architecture and your assumptions are a moving target. And people get into a habit. And they think, the right way of doing it, as we did a few years ago, is let's push everything out to the network because there's cheap computing resources there. If anybody ever gives you the option to not put something out on the network, take it. Okay? Pushing stuff out of the network when you do not need to is one of the dumbest ideas you could ever have. And there is a very simple reason for this. It's called the speed of light. It turns out it's not in a config file. You don't get to change this. This is not, you know, the point here is that we're looking at, I'm looking at this monitor here. This is about, it's nearly 3 light nanoseconds across. That's actually quite slow. If you do that in terms of cycle time, my laptop is about 1 light nanosecond across. That gives you a cycle time of around 1 gigahertz. That's really slow. You put something on the other side of the planet, that's going to be super slow. I'm not saying don't distribute, but I'm saying unless you have a very good reason to, then don't do it. And the problem is everybody's going, oh, let's push it all out. And it's just like, no, keep it all here. You can do some great things. Until somebody says, this is slow, we don't have the right clearance, or there are other reasons, then keep this. That does not change. It should be small. How small? Well, Dijkstra had this lovely way of looking at things. My point today is that if we wish to count lines of code, we should not regard them as lines produced, but as lines spent. This advice was offered in the 1970s. I was completely unaware of this advice and spent most of the 1990s advising people something similar, and this has not changed. Because it turns out that the bandwidth problem for software development and comprehension is this thing. That's the problem. Can you fit it within your cognitive bounds? Can I understand it? Therefore, can I work with it effectively? The minute you cannot do that, the minute you cannot comprehend and grasp something, then your ability to work with it drops off dramatically. It turns out that has not changed. This will never change. Well, actually, that's not true, but that's a different talk. You have to invite me back. So we see also, as an aside, that this also has benefits. Let's talk about small. This is, I'm trying to give a kind of retro feel, 1980. This is Linux, this is pre-Linux, sorry, John Lyons from University of New South Wales, if I remember correctly. He wanted to have an authentic operating system for his operating system course. And at that time, for antitrust reasons, Bell Labs and AT&T couldn't do anything with Unix. So he used that, and he put it in a book and annotated it. Or rather, he didn't put it in a book, he made a set of notes. You can see on the front, it was passed around by samizdat. People would stand at photocopying machines, copying the Lyons commentary. Now, for those of you who are too young to know what a photocopier is, it's like a socialized form of scanning, okay? And you just hang around in a university library or something, hoping to meet somebody interesting and chatting whilst you're putting this through. Anyway, it came out in book form. And things I need to observe here is the kernel code is in there. 9,500 lines. 9,500 lines gets you an operating system. I've seen classes bigger than that. And they do not do as much as an operating system. What does your system do? There, domain description. Okay, let me translate that. You take data from over here, you change the format, you do some calculations, and you put the data out over there. Is that about it? Yes. Okay. And you've got this big, honking great class in the middle of your system that seems to have its own gravitational field. It's so big. Yeah? So you've got this thing, the small thing. Computers have changed radically, and yet still it involves humans working on it, and we have limits of understanding. But it turns out also, if you want creativity, the worst thing you could ever do from a creative point of view is to take somebody, imagine an artist. Go to an artist and you say, I'd like a picture. What of? Oh, I don't know. Well, how big would you like it to be? Well, I don't know. What medium would you like me to use? I don't know. You have now got a very frustrated artist. If you start saying, I want a landscape, I want it this big, I want you to use predominantly the color blue, and I want you to do it in this, suddenly they've got something, and they will create something awesome. And this observation is true for any creative activity. As the late Dennis Ritchie and Ken Thompson observed, this paper was written in 1970. There have always been fairly severe size constraints. I love the fact that always makes it sound like it goes back a long way. Yeah, 1970. Here we are in 1970. There have always been fairly severe size constraints on the Unix OS and its software. Given the partially antagonistic desires for reasonable efficiency and expressive power, the size constraint has encouraged not only economy, but a certain elegance of design. One of the worst things you can ever do for design quality is say we have no boundaries. You need those boundaries. They're very important. Clearly, they change with time, but understand what those constraints are. Because otherwise, you end up with stuff like this. This is what we call a legacy system. This is, I took this photograph last year on Valentine's Day, because that's how my wife and I roll. That's romance. Hey, it's Valentine's Day. What should we do? Oh, let's take the kids down to Stonehenge. Yeah, that sounds great. Forget the roses. And my kids were there. They were looking at these things. I even managed to get a crow or a raven on that one. I was quite very pleased with that. So the kids were there. They were looking at them going, well, I've seen pictures of this stuff, Dad, but I didn't realize these were that big. Why is it here? And suddenly you realize that you're talking about enterprise software. Why is it here? Who built this? What is it for? We don't know, but twice a year it lines up and gives the right results. It's our job to maintain it. The reason I'm talking about this is, this is a classic information architecture. It's very grounded in hardware. And yeah, like I say, computation has come on. But, moving forward a couple of thousand years, we get to the ancient Greeks. Monolithos. One stone. One huge, sodding, great stone. Difficult to move. We don't know how to move it, but we just keep adding lichen to it and stuff, and maybe chipping away at a corner here. And you think, how do I want to build my system? In a way that is more, I don't know, aesthetic. So this is my youngest son. A few years ago, when he was about 5, he put this together, and I was very, very impressed, particularly the kind of like that little Japanese aesthetic of the seaweed on top. And you think, oh, lots of small stones, elegantly composed. That is what I want. That's a new idea. So Doug McElroy said, this is the UNIX philosophy, write programs that do one thing and do it well. I've got a lot of people going around, single responsibility principle, it's a really new idea. No, it isn't. I also show that image to a lot of people, and they go, oh, I know what you're talking about. You're talking about microservices, aren't you, Kevlin? I kind of nod, and I say, if that helps you, then yes, I am. If that's good, if that helps you, absolutely, that's what I'm talking about. Surely microservices are a new idea. Well, there is something in them that is new. But the problem is that most of the virtues that people extol about them are actually not new at all. And so here's an idea. Why don't we define a subset of the system which is small enough to bring to an operational state, then build on that subsystem? This strategy requires the system be designed in modules which can be realized, tested, and modified independently apart from the conventions for intermodular communication. So that was 1968. Okay, importantly, notice the approach here. The description is not simply of let's just put things together. There is this notion of bring to an operational state. It's not a partial system, it's bring to an operational state. And everything except for the conventions for intermodular communication can be handled and catered for. We see the same themes arising every single decade. Component software, Clemens Sikorsky, 1997. This was already old by the time this book came out as an idea. Very good definition of a component. A software component is a unit of composition with contractually specified interfaces and explicit context dependencies only. So dependency management, not a new idea again. And this concern, a software component can be deployed independently and is subject to third-party composition. Every decade, there's this beautiful cycle. It's almost in tune with the solar cycle of sunspots, which is about 11 years. There's this cycle, it goes round and round. And each wave does add something new. But the point is, you need to recognize the bit that's new, rather than say, oh, we got this totally radical. I mean, there was this really great idea called service-oriented architecture. And the difference between services and microservices is the word micro. Because it turns out that when you look at the definitions of what services are supposed to be, they're kind of an awful lot like what people are saying microservices should be. Oh, they should be small, composable, and you can have a small team, and you can do this, and you can update them independently, and then they grow. Yeah, micro is turning into milli, is turning into centi, and is eventually going to turn into macro. So, it should be small. It should be interoperate with the programs and tools the expected users are already using. Everybody likes to reinvent the universe. The full quote for Doug McElroy is this: write programs to work together. Interoperation. Of course, John Cook made this wonderful observation in McElroy's summary. The hard part is his second sentence: write programs to work together. That is non-trivial. That is one of the reasons that we end up with bloat and challenges, and that's a human thing. That's not going to change. So therefore, exactly the same challenges that we have always had will always be present. Things they lose scope, they drift a bit, they get a bit bigger than they should be. We end up with a lot of fudge code and sort of workarounds to get things to talk to one another. That's not going to change. Perhaps what you can change is your awareness that that is constant. It should be bug-free, and if that requires implementing fewer features, do it. Okay, well, there's many ways of ensuring that we could actually try and do stuff and make sure it works. One of the things, it's a radical idea that's proven popular, testing. So Alan Perlis in 1968, a software system can best be designed if the testing is interlaced with the designing instead of being used after the design. One of the things that I found fascinating about reading the software engineering proceedings from 1968 was there were some terms that I had assumed came around later. For example, middleware. I had originally attributed to late 70s, early 80s. The term middleware is in the document. Unit tests, I had attributed as a 1970s term. I'd been unable to find anything predating the 1970s until I read this document. So this is not news. You might say, oh, okay, well, maybe we're going to talk about test-driven development. Surely that's new. So Alfred Aho, who is the A in Orc, Aho, Weinberger, Kernighan. Orc is a lovely little language that doesn't get as much, perhaps doesn't get as much airtime as it used to, because everybody scripts and stuff these days. But it was partly knocked out by that abomination that people call Perl, or as a friend of mine described it, executable line noise. And Orc has a very elegant and counterintuitive execution model. It's organized around pattern matching and goals, and it's some really nice little stuff. And so in an interview, so it's 1970s, Alfred Aho says, we instituted a rigorous regression test for all the features of Orc. Any of the three of us, Aho, Weinberger, or Kernighan, who put in a new feature into the language first had to write a test for the new feature. So there you go, TDD 1970 style. We are very good at reinventing stuff. Sure, our motivation and our understanding of things improves, but we need to understand that a lot of these ideas that are treated as new are not. And if we only had the ability to recognize this kind of constancy of old ideas, we'd probably get even further with our refinements and understandings. While we're on it, and I know Dan's in the audience, given when then, my favorite way of describing test structure, as well as organizing requirements, also has echoes. I remember looking at that going like, wait a minute, this is how I used to do use cases. Preconditions, triggers, postconditions. But it was Jason Gorman that tipped me off on the fact that this is Tony Hoare's logical construct, axiomatic basis for computer programming, 1969. Given a precondition, when you execute something, you get a postcondition. And this was the basis of formal methods, but it also turns out to be a good conversational construct, a good way of organizing tests. It's recursive. It's present all the way through. This is not, in that sense, a new idea. I'm just looking forward to the 2020s when we'll probably find a different way of describing these three. It should use parsimonious abstractions as long as they don't get in the way. So don't make things too complicated. So Ward Cunningham came up with the term technical debt. That one dates back to 1992 as a term. And a lot of people misunderstood what Ward was saying. He wasn't saying it all sucks. Because, I mean, I have a debt. My wife and I have a debt. It's called a mortgage. Yeah, the clue to the word mortgage is actually in the first word, first part of it, mort, death. This is a deal unto the death. Okay? Now, it turns out we get a decent trade-off for that. We've got a mortgage. It's structured debt. People don't turn up on our door with brickbats saying, give us the money every month. It's structured. We've got a reasonable way of repaying it. And in exchange, awesome, we get a house. So in other words, debt is not of itself bad. It's what you do with it. And as far as Ward was concerned, he said, shipping first-time code is like going into debt. A little debt speeds development so long as it is paid back promptly with a rewrite. I think Ward is very conscientious with his money. He couldn't imagine that anybody would say, yep, let's just increase the debt. He says he coined it so it would be blindingly obvious that it's a bad idea when you leave it unmanaged. The danger occurs when the debt is not repaid. Every minute spent on not quite right code counts as interest on that debt. Now, importantly, that was the origin of this. But again, the observation that sometimes it doesn't work out quite as we hoped dates back even further. There you go, that's microservices architecture, as implemented by most companies. Alan Perlis, in the long run, every program becomes Rococo and then rubble. If you're not sure what Rococo is, it makes Baroque look minimal. So we are presented once again with this idea of like, okay, so how do you build a system? Surely we can just specify it and it'll all work. It's just the programming that's getting in the way. Edward Berard, 1991, I think. Walking on water and developing software from a specification are easier, both are frozen. So how are we going to do this specification? So one of my favorite cartoons, alongside XKCD, of course, is Commit Strip. And you have the manager talking to the coder there. Someday we won't even need coders anymore. We'll be able to just write the specification, the program will write itself. Nobody's ever said that at all in the history of programming, going back to the 1950s. Yeah, again, there's a regularity. Maybe people could just write that, and you watch it come around again. Oh, wow, you're right. We'll be able to write a comprehensive and precise spec, and bam, we won't need programmers anymore. Exactly. And do you know the industry term for a project specification that is comprehensive and precise enough to generate a program? Code. It's called code. You can't get much more precise than that. Jack Reeves in '92, C++ User Journal. This is actually a touchstone for many of the craftsmanship movement. And again, this is considered to be, this is over 25 years ago, and there's this idea, and it wasn't necessarily new, but he crystallized it wonderfully in this exploration of what is software design. Programming is a design activity. Now, why is this important? It's important because for decades, and we continue to do it, I'd like to say it's all in the past, but that's not the case, people have managed and mismanaged the programming activity as if it were non-intellectual, non-design-based, and merely a production activity. And this idea that it's not a production activity is not new. It turns out that we've solved the production problem. It turns out that there are other engineering professions that are deeply jealous. Now, again, this is not a new insight. 1968, Peter Nauer and Brian Randall. The replication of multiple copies of a software system is the phase of software manufacture which corresponds to the production phase in other areas of engineering. It is accomplished by simple copying operations and constitutes only a minute fraction of the cost of software manufacture. This is a profoundly unoriginal observation. But but we keep going, every time I think, oh, it's a new observation. I remember first coming across it in the 1990s, Jack Reeves. Every time I look further back, there's somebody else who said it. And this is important because if you manage the design activity, you're going to manage something very different to managing the production activity. So how are we going to organize stuff? If it's a programming activity, it's a design activity. Parnassus, 1972. Again, this one's a sort of a standard classic, especially everybody going into phases and getting very excited about modular concepts on its usual cycle. The Java folks are getting excited about this one again, having forgotten they already had classes and stuff like that. But nonetheless, Parnassus said, we propose that one begins with a list of difficult design decisions or design decisions which are likely to change. Now notice he's not organizing abstractions by, necessarily domain. He's not organizing them by this idea of how things group and cluster or normalization. He's organizing them by volatility, by certainty, by stability and instability. The recognition that change is the only constant has always been there. And perhaps when you are creating a software structure, one of the things you need to care about is not simply the cognitive bandwidth of a human being, but the economic ramifications of what happens if we have to keep changing everything. If I have to touch everything all of the time, that's going to be an unsustainable activity. I won't end up touching everything all of the time. I'll just touch a few things, and then everything will localize, and then we'll end up with Stonehenge. And we'll end up with a lot of copy and paste. Actually, you can't do that with stones, it turns out. But each module is then designed to hide such a decision from the other. This simple observation crystallizes many things, not simply the idea of modularity, but most people overlook that his observation was to do with volatility. You've got a team that can't agree on a design, guess what? Put a boundary around that disagreement. You can actually come up with a really simple draft of how to structure your system based on whether or not you agree with your colleagues. Yeah? Based on, hey, we've got 2 ideas for this, okay? We've got something there. We have no idea about this. Okay, well, there's a boundary around that. You can actually structure a system, first draft, let's try that. It also tells you how your process can flow, where you're going to explore. So, Cohesion, one of my favorite books, picked this one up in Powell's in Portland. People just don't do book covers like this anymore. And there's probably a reason for that. This is the 1970s. And, you know, depends on what people were taking at the time. But that does something to your eyes. Cohesion is a measure of the strength of association of the elements inside a module. A highly cohesive module is a collection of statements and data items that should be treated as a whole because they are so closely related. Again, we've got a different perspective on why we glue things together. Any attempt to divide them up would only result in increased coupling and decreased readability. Not a single concern that we express now seems even remotely new. So let's talk about other things. Let's talk about our understandings and misunderstandings of paradigms. Alan Kay, who I mentioned earlier on, his perspective on object orientation was this. It means only messaging, local retention, and protection and hiding of state process, and extreme late binding of all things. Now, what I find interesting about this is that when you look at this, it tells you, wait a minute, this is a messaging model at heart. And in this book that I edited a few years back, 97 Things Every Programmer Should Know, Russell Winder makes this very simple observation. He says, right, okay, instead of using threads and shared memory as our programming model, we can use processes and message passing. Process here just means a protected independent state with executing code, not necessarily an OS process. But it turns out these ideas are fairly old. Languages such as Erlang and Occam before it have shown processes are a very successful mechanism for programming concurrent and parallel systems. They don't have all the synchronization stresses that shared memory multi-threaded systems have. The problem is that we got all very excited about adding threads to code, and everybody sort of said, yeah, let's go and add this stuff into our core programming languages and core libraries. And I remember when Java came out, that one of the first things I noticed about it was that all of the collection classes, the few that it had these synchronized interfaces. And I remember thinking, you guys have no idea what you're doing, do you? Because that's not how this works. The active thing you don't want to do is to share raw primitive collections between threads. You're just doing threads because it sounds cool. And this is the problem. The rest is history and consultancy and bugs. Always remember, if you're trying to improve performance, then a thread is not the way, composing in terms of threads and locks is not the way to do it. Synchronization is the one thing you actively want to avoid if possible. All computers wait at the same speed. Yeah? You can have a 3 gigahertz wait, you can have multi-core wait. Yeah? That is the purpose of synchronization. It is to stop. The purpose of synchronization is to eliminate concurrency. So if somebody says, we're doing threads to make things faster, why are you using locks? To make things slower. I sense a disturbance in your understanding of the forces involved. So this is not new. I mean, the actor model actually dates back, Carl Hewitt, 1972, 1973. Occam, which is based on communicating sequential processes. Hey, Tony Hoare again, 1970s is its origin. I ended up doing some stuff with Occam a few years ago. I also ended up doing a master's degree where my research was about the actor model, this rather than something like Erlang. And so it was object-based, but it was also built in Lisp, which was kind of interesting. And this kind of brings us around full circle, because what we've just done is we've accidentally noted that, and if we look at what Alan Kay used to say about Smalltalk and the relationship to Lisp, he said that it was quite tight in the sense that the idea of building a system where around a small set of primitives, a small set of ideas from which you can compose something larger, he got from Lisp. And that inspired Smalltalk. It was actually an economy of ideas that went through. But the messaging model, that also seems to be interesting. And people debate whether or not actors are an object model or not. The reason they do this is because it's politically interesting to debate it. There is no debate. They are an object model, according to the original definition from Alan Kay. And it turns out that lambdas also fall into this. There's a wonderful paper written in 1984 by Cardelli and Regner about data abstraction. William Cook revisited it a few years ago, saying, let's actually explore the theoretical basis of this approach. And he makes this observation. Lambda calculus was the first object-oriented language. And he puts the date in 1941, so I did a bit of digging. 1932. So it's kind of like really sweet when you've got Java programmers getting terribly excited in 2014, going, yay, we've got lambdas. And you've got the C++ programmers going, like, we got those in 2011. And you've got the JavaScript programmers going, yeah, what about us? And everybody else is going, yeah, what about you? We're talking programming languages here, right? And then you're sitting there and you've got all this conversation. You've got Lisp and Algol sitting there going, we had those 1960s, 1932. Yeah? Programming like it's the 1930s. However, obviously, everybody gets a little bit, go, oh, this is the best paradigm, this is the best paradigm. I always like to bring functional programmers down to earth with this observation from Mr. Haskell, Simon Peyton-Jones. Excel is the world's most popular functional language. It tells you that half of the story is not the paradigm, it's how you execute it. It's how well it is carried out. And it is slightly galling to many people that people in their accountancy department have been doing functional programming for far longer than they have. But we have so many misunderstandings. It turns out that this is a landscape without boundaries. There's a continuous flow from one paradigm into the next. They're not bordered off. Nobody's built walls between the paradigms. That's a stupid way of thinking. So we're going to separate everything else apart. Modularity, lambdas, whatever it is. But we do have to put all this back together again. And that becomes our perspective on this one. We have to have a philosophy of this, and perhaps that philosophy we like to call architecture. But there's a nice way of describing how we should be reasoning about larger systems, and this also takes us into the modern space when we need to start thinking about how we compose microservice systems, how we compose, how we organize our reasoning about frameworks. Back in early 90s, Galernta and co. Talked about coordination languages. And I remember learning about this stuff. It made a lot of sense to me, this idea of a genuine separation. We can build a complete programming model out of two separate pieces, the computation model and the coordination model. You have nice little pieces that do nice, well-specified jobs. Again, this predates component thinking, but that idea, the same cohesive idea, and then you have separate to that a coordination model. And sometimes it helps if it's in a different language. People find that more convenient, but it doesn't have to be. But how old is the oldest coordination model? Well, I've noticed one thing at this conference, and I saw it in a tweet. Somebody observed, you know what? Everybody keeps referring to UNIX pipes. So yeah, so will I, 1964. Doug McElroy again. We should have some ways of coupling programs like garden hoses, screw in another segment when it becomes necessary to massage the data in another way. This is the way of I/O also. What you have here is a concatenative programming model, a functional model, a data flow model. And this was conceived of in 1964, the idea of the coordination model. I'm going to have processes that have a very simple input-output model, continuous, so ongoing execution, not termination-based execution. You run a program, then it finishes. Ongoing, and then I'm going to have a coordination model, the pipe. It took 6 years to find the pipe symbol on the keyboard. It was Ken Thompson that found it, 1970, put it in. So sometimes a good idea takes a while to implement, 6 years in this case. So I want to close on this idea that we know in many ways more than we give ourselves credit for, and that brilliant as our progress has been, we might be even better if we paid attention to the things in the past, so we could understand when a new idea comes along, what is genuinely new about it, and focus on that, rather than getting distracted by repeating the same message, copying and pasting exactly what was, literally copying and pasting. I worked with a guy a number of years ago who had a same PowerPoint presentation that every time a paradigm came along, he would get the PowerPoint presentation and just do a global replace of whatever word, object for component, component to service, service to microservice, whatever. He would just do a global replace and go out to customers and say, look, this is what we're offering you, okay? So the point here is that these are the things that are timeless, not just the constancy of PowerPoint. That at one level is cynical, but it's also actually revealing. But we would make much more progress if we had this kind of historical recognition that there do seem to be these core ideas. Thank you very much.